So this is joint work with Daniel Genkin, Manoj Prabhakaran, Eran Tomer, and Amit Sahai. And as the title suggests, the talk will be divided into two parts. For the non-cryptographers in the audience, I guess that the first part, which talks about a new model for fault-tolerant circuits, will be more interesting. And the second part of the talk will deal with how to protect cryptographic protocols against active attacks or malicious parties. And the connection between the two parts, as you might guess, is that the first problem motivates or is used to get the second solutions to the second problem. Okay, so let me start by talking a bit about fault-tolerant circuits. And if you think naively about the problem, right, we have here some Boolean circuit that maps an input x to an output f of x. And naively, what one might hope to achieve is to have this circuit resist all kinds of torture and yet output the correct answer, right? So this is Galileo Galilei. And he is very insistent. He resists all kinds of torture, and that's what we really want to get. But in reality, that's maybe a bit too much to hope for. In particular, this attack usually works. Keep in mind that Galileo Galilei is an Italian. Right? I'm not sure if you can see. That's an envelope with cash. And of course, you know, he's an Italian. Here in the Holy City, such things could never happen, of course. But anyway, that's a simple attack that shows us that really you can directly attack the output of the computation, and therefore you cannot really hope to protect it against any type of torture, an arbitrary torture. So in the literature, there have been various approaches for relaxing this ambitious goal. The classical one, originating from von Neumann and perhaps culminating in well-known works of Pippinger, assume that every gate fails with some small constant probability, and then the goal is for the output to be correct with high probability. Right? And there's been some really nice and non-trivial work showing how to get efficient constructions of fault-tolerant circuits in this model. There have been other types of models which, instead of assuming the faults to be random and independent, just bound the total number of faults, say, in each layer in the circuit or in each pass from an input to an output. And this relaxation also turns out to be useful. The goal we pursue in this work is to try and protect circuits against an arbitrary number of faults that can affect every part of the circuit. For this, we're making some pretty benign relaxations. First, we're allowing the circuit to be randomized, to have randomness gates. Second, we might settle just for detecting errors with high probability, where the probability is over the randomness of the circuit. Okay, so these are, you know, natural relaxations, but still, these relaxations of the goal still don't seem to be sufficient because they don't rule out, for instance, directly messing with the input or the output, which will again defeat the purpose of protecting the output. So, motivated by this, we make two additional relaxations. First, as I said, we want to prevent direct attacks on the input and the output, so we allow the input to be encoded by a tamper-proof input encoder, and the output to be decoded by a tamper-proof output decoder DEC. And to rule out trivial solutions where, say, the decoder does the entire computation, it's tamper-proof, so why not let the decoder do the computation? We require these encoder and decoder to be universal, namely they depend only on the size of the input and output, and we also want them to be small, namely of size polynomial in the input and output respectively. And this rules out delegating all of the work, the computational work, to the input encoder or the output decoder. Okay, but still this relaxation alone is also not enough, because instead of now we cannot directly attack the input, but we can attack all wires say, coming out of the input encoder or all outputs entering the output decoder and fix the output to something that looks legal but wrong. Okay, so the final relaxation we're making is, again, that's a natural relaxation from a TCS perspective, is to consider a restricted class of faults. And the type of faults on which we focus in this work is additive attacks that can apply to every wire in the circuit. By additive attack, in the Boolean case, this just means, so a Boolean, a binary value can be viewed as a value in the binary field, so adding something to an element in the binary field is just negating, right? So an additive attack in the Boolean case will just mean that the attacker can pick an arbitrary subset of the wires and put a NOT gate on these wires. And we will also be very interested in the case of arithmetic circuits. So arithmetic circuits take inputs from a finite field, and they can add, subtract, and multiply field elements. That's a natural generalization of the Boolean circuit model. Boolean circuits can be viewed as arithmetic circuits over the binary field. And in this case, an additive attack is just what it sounds like. You can add some fixed field element obliviously to the values of the wires. You just choose by how much you want to change or how much you want to add to the value in each wire. Okay, any questions about the attack model? Yes? Yes, so if you want to, as I said, the attack I said before, of just fixing the values that feed into the input decoder. But you can pick something that the decoder accepts. Again, we're not using crypto here. You can fix it. No, the encoder and the encoder is randomized. The decoder can be deterministic. I mean, it is deterministic in our model. Yes.
So if you restrict yourself to additive, is it clear that you need the tamper-proof encoding and decoding?
If I restrict myself to additive, yes, because otherwise you could. I will talk about another definition which doesn't need it, but if you insist on outputting the correct output, you need to rule out just adding one to the output or adding one to some input. Okay, if I want to insist on getting either right, so our goal is to detect error, so I want to either output the correct output or to indicate that I detected an error. Okay, so before we ask, questions, new questions about computing or fault-tolerant computing, we should try to see what is known about the same questions in the simpler domain of coding, right? Of just keeping information alive as opposed to manipulating information. And it turns out that this type of encoding that detects additive attack has been considered. It might have been considered before in other communities, but in the theoretical computer science community, there was a paper of Kramer et al. That initiated the study of so-called algebraic manipulation detection codes. These codes were defined over a group. We work over fields in the arithmetic circuit model, but so in our case, A will stand for additive as opposed to algebraic, but still, this is an analogous notion for coding, right? So an AMD code also has an encoder and a decoder, and it should, basically, it corresponds to a special case of our notion where the circuit is just a trivial identity circuit. Okay, so this notion has been studied and it can be realized. Actually, it's quite easy to realize. Okay, and what we want can be viewed as an analog of AMD codes, which we refer to as AMD circuits. So instead of protecting information against additive attack, our goal is to protect computation against additive attacks. Okay, and that's the name I'll use, AMD circuits. Okay, so let me be a bit more formal. Again, we consider a function that maps n field elements to m field elements. We have an encoder which can be randomized or has to be randomized. We have a randomized circuit C, which is an arithmetic circuit over the field, and we have a deterministic decoder. And we say that this triple ENC-CDEC realizes f with epsilon correctness. Epsilon, when it tends to 0, it means that it's almost perfect. It gets better. So epsilon correctness means that if you first apply the encoder, okay, that's first the kind of a completeness requirement. It just means that if there is no attack, then you always output f of x. And the correctness requirement says that if you let the CA be an arbitrary circuit that is obtained via this type of an additive attack, then the result of running the encoder, then the attacked circuit, and then the decoder will be either the correct output or E, which is a flag that is set to some non-zero value to detect error. And this should hold except with probability error, except with epsilon probability. Okay, we want everything to be arithmetic, so this is why we assign we don't want it to just be a bit, it's a field element. Yes?
The C of A doesn't depend on X, right?
The C of A, yes. The attack is always blind. You fix a value, it depends only on the identity of the wire and not on the value of the wire. Okay, and as actually Tal suggested, in crypto we're used to doing the impossible by just relaxing the ideal model, right? Or relaxing our expectations. So you could in fact consider a similar model that has no input encoder, no output decoder, and in this model the best we can hope for is to push the internal attacks to the inputs and outputs, right? This model, it's inevitable. You can always attack the inputs and the outputs, and what we want to achieve is that, you know, if you have any additive attack on the internal wires, it can be simulated, or the effect of this attack on the input-output relation can be achieved by a possibly randomized additive attack on the inputs and outputs alone. So that's like a usual real ideal in crypto. And this effectively means that the circuit, from the point of view, or when considering additive attack, is just as good as a piece of tamper-proof hardware that computes the same function. Right? The tamper-proof hardware, you can also attack the inputs and outputs. You cannot attack anything inside it. Okay, so this is actually a cleaner notion, and it turns out that it's also a more useful notion, but let me first define it formally. So again, in this audience, most people you know, can guess how the definition looks like, but we refer to this as epsilon security, as opposed to correctness, which was the previous definition. And we say that C is an epsilon secure realization of F if, first of all, you know, it always outputs F when not subject to attacks. And second, for every CA that's obtained from C via an additive attack, we have some distributions delta X, which is what we add to the inputs, and delta Y, which is what we add to the output, such that the output of the attacked circuit is like, that's the ideal model. Right, C, I could write F instead of C, it's the same. Okay, and why is this definition more useful? Because it's not hard to take a general solution for epsilon security and get a general solution for epsilon correctness. The idea is just to protect the inputs and outputs via an AMD code. Right, so suppose that I have a general solution that turns any function or any circuit into a secure circuit where the inputs and outputs can be protected. Then I can have this seemingly redundant way of computing the function, right? I first apply A-enc and A-dec are just encoder and decoder of AMD codes. So I basically do this redundant encoding and decoding of the input. Then I apply the function I want to compute. Then I do an encoding and decoding of the output. The only subtlety is that I need to pass the error flag of the first AMD decoder and let the second AMD decoder output set this flag if either this flag, which was encoded, was set, or the flag is set inside the second decoder, right? So that's just some kind of error propagation mechanism. But why am I doing these redundant steps? The reason I'm doing it is that now I can define a new function f prime and apply a secure AMD circuit that realizes this f prime. And now this f prime cannot be attacked, and all the adversary is left with is attacking these AMD encoded input and output, which it cannot change. It cannot tamper with, any tampering will be detected. And the useful feature that was not guaranteed and in fact will not be satisfied by the previous epsilon correctness definition. I mean, okay, the epsilon correctness definition does not rule out the possibility that setting the error flag is correlated with the input. Right? So ideally we want that the error flag, whether it's set or not, only depends on the type of attack and we don't want this error flag, at least for cryptographic purposes, we don't want this error flag to be correlated with the input. The correctness definition just said that the output is either error or the correct output. It doesn't talk about what information this error conveys, which again is something that people, cryptographers are well familiar with. The security definition, on the other hand, if we apply it together with a strong AMD code, the strong AMD code is the one that also satisfies this lack of correlation property, that if you tamper with the encoding, then an error will be detected with high probability, no matter what the input is. So if you use this type of strong AMD code, this concatenated construction will satisfy this, will have this feature, okay, which will turn out to be useful for the applications. Okay, any questions about the definitions? Okay. Like up to epsilon indistinguishability. Okay, so let me tell you about our results for this part of the talk. So we have two distinct, very distinct constructions, one that works well, one that's considerably simpler and works well over large fields, and one that works over arbitrary fields, in particular the binary field. So the large field construction, it takes an arbitrary arithmetic circuit, which computes some function f, and builds an epsilon secure version of this circuit whose size is only a constant times bigger. And the error probability is something like circuit size divided by the field size. So if the field, the field element is 100 bits long, then this will be secure enough for all our purposes. For the case of small fields, in particular, if you consider the case of Boolean circuits, where we need to use a binary field, there we get a weaker result, which only gives this epsilon correctness and also does not eliminate the correlations I discussed between the input and setting the error flag. And also the overhead now is not constant. The multiplicative overhead is polylog in 1 over epsilon. Right, so these are the two types of constructions. Let me give you a quick overview of the idea. So the idea for the case of large fields is fairly natural. We use a kind of a homomorphic AMD encoding of the inputs. Right, so you randomly map X into the triple X, R. R is a random field element, and X times R. This is not a strong AMD code in the sense that you can correlate the event of detecting error with the input. Right? If the input is 0, then you can add whatever you want to the second entry without triggering a flag. So it's not a strong AMD code, and this will be somewhat problematic, but it does satisfy the more liberal notion of AMD codes. And now we can multiply and add these triplets in a natural way, keeping in mind that the degree, so they're all encoded with the same R, and the degree can grow. So if we multiply pointwise. So again, we have this kind of authenticated triple where now R squared is used as the second entry. So the degree in R grows. Right, so in general, we can multiply triplets that are authenticated with different degrees, and then the degree grows accordingly. When we add things, right, if R has the same degree, then again we just add the first and third entries, and again we have this property that the product of the first two entries is equal to the third. That's the checking of the code. And in general, we need to align the degrees before we do the addition. So we need to multiply by some power of R. And how do we, I mean, we want to get a secure construction which should output the output in the clear, so we don't have some decoder, so we need to actually output, convert a triplet to a single field element. So there we just use the standard trick of S is a random field element. This polynomial is equal to 0 if and only if Z is equal to the product of the first two entries. And so this will have the effect that if the triple is invalid, the output will be completely random, which corresponds to a valid attack. Yes?
Just a short question. What in the addition are you multiplying in the second line?
What?
In the addition, you're multiplying in the second line when you're taking the max of B and D prime. You're multiplying A times B.
Sorry, that's a typo.
Okay.
This should be A plus B. Sorry, yeah, it's a typo. Okay, so there are two problems with this approach. So it can be analyzed. It basically works using, you know, what you might expect, Schwartz-Zippel or standard tools. But there are two problems. One is that the degree in R grows, and it can grow exponentially with the size of the circuit. And so, you know, the error grows linearly with the degree, so we cannot really afford to use this construction for deep circuits. The circuits should have a small degree compared to the size of the field. And the second construction has to do with this correlation problem I alluded to, that, for instance, if you add 1 to the second entry of an input, you will cause an error if and only if the input is non-zero, which is not something we want or we can simulate. And therefore, we need to apply some pre-processing step to the circuit to make it locally random, okay, to ensure that there is some technical requirement of local randomness that can be achieved using standard approaches. Okay, and this will make sure that we don't encounter these correlations. Okay, for the small fields, the construction is more involved and also more ad hoc. I guess we're still missing the right way of doing it. First, we have an ad hoc, a fairly simple and ad hoc construction that achieves matrix vector multiplication. Then we use this as an atomic building block in a more complex construction that essentially implements the linear PCP of ALMSS, the Hadamard-based PCP. So when you consider standard PCPs, the verifier is expected to be honest, right? So PCPs, this type of PCPs does provide a protection of the verifier against additive attacks on the prover, but here we also attack the verifier algorithm, and therefore the analysis of this is quite ad hoc, but it turns out that it works. And the two problems of this construction, so this construction is a direct construction. It can directly handle a circuit as large as you like. There are two problems with this construction. First, that it has a constant error probability. Second, it has quadratic overhead in the circuit size. And we get around both of these problems in fairly standard way. So, of course, to drive down the error probability, we use repetition. Repetition here turns out to be a bit tricky, because for technical reasons, for the next step that I will describe, we need to use a version of this that does not protect the input by an input encoder. And this raises the possibility that we are amplifying on different inputs. That the attacker can basically, if you repeat the same computation, you'd better repeat it on the same input, or else just the amplification will not work. So we need to also use a tamper-proof computation of some small hash of the input to ensure that all computations were done on the same input, and then the amplification step works. And to get rid of the quadratic overhead, we use a bootstrapping approach that was used before, say, in a work by Nir and others, and also it's somewhat reminiscent of the FHE bootstrapping of using a small, so we basically apply the construction to a small circuit that does some decoding and then a computation, and we build the circuit by using many such small gadgets. Yeah. Okay. Okay, so I will talk briefly about the second part, which is, the main points here are just the high-level points. So secure multi-party computation, you basically know what it is, I guess, right? There are several parties that want to compute some function of the input. Some of these parties may be corrupted, and the goal is to have protect the secrecy of the inputs and the correctness of the output to the extent possible, or emulate an ideal function evaluation process using a trusted party. We have these classical results, which can be divided into two parts. Here I will focus on those results that talk about information theoretic security. So information theoretic security you can get either if you assume an honest majority, or if you assume some hybrid model like an oblivious transfer or its generalization called OLE. And these hybrid models can later be implemented by efficient computationally secure protocols. So if we do have information theoretic crypto with no honest majority, assuming the right hybrid model, and then we can implement the hybrid model. So these are the two settings I will talk about. And let me guess that the crux of this talk, that's probably the most important slide in the talk, is that this model of fault-tolerant circuits is motivated by a new approach for converting protocols that are secure against passive attacks or semi-honest parties into protocols that are secure against malicious parties. That's a major problem in crypto. We have different, like the GMW paradigm. We have many different approaches for this, but all of them are quite involved. And what we observed, that's the main observation, is that if you take most natural protocols in this setting of information theoretic security, then take the protocol that is very simple and was designed to protect against passive attacks. If you actively attack this protocol, then all you can achieve can be modeled by additive attacks on the circuit that the protocol evaluates. So you can actually formalize it by saying that, say, the semi-honest GMW or the semi-honest BGW, these protocols, in the presence of an active attacker, they perfectly realize a relaxed ideal functionality which allows the adversary to have an additive attack on every wire. And on every wire, yeah. So this basically applies to all of the protocols that achieve optimal security threshold in their model. So either using a hybrid model, so tolerating any number of corrupted parties or tolerating an honest majority. And then basically it reduces the design of moving from semi-honest model to malicious model to the design of an AMD circuit for the functionality that you want to compute. And we have applications. So there is technicality. We need to protect the input and output, and we do it like I did before when moving from security to correctness. And there is an issue of guaranteeing output delivery. So the protocol only detects faults and doesn't tell you even who is guilty, but you can get around it using standard techniques. And the upshot of all this is that we can simplify some feasibility results from the area and get some asymptotic efficiency improvements, and also some somewhat esoteric but apparently new feasibility result for preprocessing with potentially faulty preprocessing. Okay, so let me conclude. So introduce this notion of AMD circuits. There are quite a few open questions, both in terms of efficiency and in terms of feasibility. And also in the MPC applications, it would be nice to extend and also unify the class of protocols that we can use this approach on. That's it.